Hey there, everyone. My name is Ryan Schul. Welcome to my data science channel. And the topic today, I want to talk about a project where we are going to use strategy, resource allocation, and optimize the effort and labor that goes into the process. Okay, so I have several videos about optimization. I can do more if you guys like it. This is a very interesting topic, and I like it a lot. So I've got portfolio optimization, I've got workforce optimization, things like that. So you can check it out on the channel. And the reason we do this is to maximize ROI. This is the return on the investment, right? It's a financial term. I got my MBA in finance about 22 years ago or 21 years ago from Johns Hopkins. So I'm very intimate and very familiar with the topic of ROI. We want to prioritize high impact strategies, balance risk and rewards, right? Like lower risk and improve rewards, avoid resource over allocation or under allocation. It could go either way. Scenario planning, we want to plan ahead of time and understand what's going to happen in advance before we actually do it. We don't want to just blindly run into a scenario with no anticipation or understanding what's going on whatsoever. You don't want to do that. We want to be transparent and make data-driven decisions so we can make more intelligent discoveries, right? And more intelligent decision-making activities and align teams across departments. So I worked on Wall Street for something like 22 years. And you see these silos, like this team does this, and this one does this, and this other does this, and this guy does this over here, right? But they're all like misaligned. They're not integrated. They're not cohesive. They're not collaborating whatsoever. That makes me sad. I mean, I get sad, I get depressed when I see things like that, but it's everywhere. We want to try to avoid these scenarios, right? We want to be more integrated, more adaptive, more anticipative, and more collaborative. That's the goal here, okay? So I created a synthetic data set because I couldn't find exactly what I wanted to do online. I searched a little bit, but I'm kind of a lazy person. I couldn't find it, so I just gave up and just created my own. So we have here department, strategy type, expected benefit in terms of dollars or cost, right? Required budget, and then headcount required for the work, right? There's always work, there's always effort, there's always labor that goes into everything, right? So how many people do we need to achieve the objective? And we want to do resource allocation and optimization, right? So the goal here, the total budget is $200,000, right? 200,000 American dollars, and we're using 25 FTEs. This is a full-time employee, okay? So how are you going to align your resources, which is the FTE, that's the person, and the budget, and achieve the mission that you're targeting or that you're aiming? How are you going to do that? So we're going to look at an optimization allocation strategy here using linear programming, or PULP. PULP is linear programming. So I studied this in grad school. It's like if you have an XY axis, like how much can you go up, how much can you go down, how much resources can you contribute to this, or if you take resources away from this objective and reallocate it to another objective, right? Like you're going to have an increase in the other area. So how do you combine all these things together? It's like putting everything into a blender. You have your strawberries and your blueberries and like a little cup of ice and a little bit of whipped cream and blend it up and make it a smoothie or something like that, right? How do you optimize that when you blend everything together, but you want to achieve a certain objective outcome, right? So the PULP library is going to help us with that. Again, we have 200,000 budget and 25 full-time employees that we can allocate for the task at hand here. So I'm going to set up these requirements. There's going to be constraints, right? Like 200,000 is a constraint. 25 employees is a constraint. You have to set up these constraints right here. Here's the budget, and here's the head count. It has to be less than the budget, and the head count has to be less than the head count, right? So when we run this, we get the strategy type, benefit, required head count, okay, and selected. Is this going to be selected yes or no? So that's what we're trying to prove or to achieve right here. So the total budget is going to be X number of dollars, right? And the total outcome is going to be X number of dollars. And the resource allocation number of people that we have working for us is going to be limited too, right? There's always limitations whenever you do. There's limited time, limited money, limited resources with whatever you are going to do, okay? So when we optimize the whole process here, we can see the total benefit is 1.325 million, okay? And the capital use is 488,000, right? This is called capital creation. This capital destruction, you see this all the time in the news. People are investing a lot of money and you don't get any payoff or any payback, or like a minimal payback. You can invest $1 million and get 20,000 payoff, ROI, return on investment, whatever you want to call it, right? That's a capital destruction. This is capital creation. So we try to create a bigger benefit and more value added based on the synergies, right, of the resources on the team and the overall enterprise, this company that we work for, right? So we invested 488K, we made 1.325 million, sorry. So over 100%, I don't know what this is offhand, like maybe 120%, 130%, something like that. So definitely pays off, but only because we optimized the whole process and we put money in 488,000. We made 1.325 million, right? So this is definitely a win. This is definitely a process that we should invest in, and a business that we should engage in, or a project that we should engage in, right? But only because of the linear programming, right? So we tried to optimize the process using Pulp, the Pulp library from Python, right? And there's a couple libraries. There's Pulp, there's SciPy Optimize, and GarobiPy, and I think there's a couple others. I've used those three pretty definitively, but I think there's one or two others maybe that you can use. So there's other ways to do this, but Pulp is really the best because it's very straightforward. It's very linear, right? That's why we're using a linear programming solution here. We have the strategy type, the expected benefit, the required budget, required headcount. It's very straightforward. Like you put in this much, you get out this much, okay? This is equal. Not equal. This is a very easy problem to try to solve. If the problem is more non-linear, you might need more of a SciPy Optimize or GarobiPy, which are non-linear discovery processes to optimize a solution, right, that you're engaging in. But this one's pretty straightforward. It's very linear, so we're just using a linear solution. It's a linear problem, linear solution. So let's look at the before and after. So the before optimization, expected benefit 2.42 million, and the optimized benefit 1.32 million. And when I set this up, like I'm looking at all the logic and all the code, this made sense to me basically, but it was a little bit confusing too because you're using total expected benefit before optimization, right? And what is the payoff after optimization? It's all the sum of all possible benefits from all the initiatives, assuming that you could do everything, right? So we have this scenario where we have the department strategy type, expected benefit, expected required budget, and headcount, right? So should we engage in this project or should we not? So this shows you the actual payoff, the before optimization and the after, right? But actually decrease. So why would we actually engage in this kind of process if after we optimize everything, we have an expected benefit decrease, right? Like at first, it was a little bit confusing, but I figured it out pretty quick. The total expected benefit after optimization is the sum of all the benefits only from the selected initiatives, given the budget and headcount constraints, right? So you can invest in everything that you want, but you can spend your entire budget and utilize all your resources, right? So the headcount is going to be more than 39, right? You're going to have probably, 50 or 60 people. You invested $488,000. You made 1.325. So this is a win. It's an absolute win, right? This is a win-win. You made money and you minimized the labor investment, which is 39. Otherwise, it could be 50, 60, who knows how much, right? But you spend 488K, made 1.325 mil, right? And the benefits are obvious. There's optimization because the optimizer is restricted into what it can choose. So it's not going to choose every single project. You can invest every single project and invest 1.3 million, right? But if you invest 1.3 million and you make 1.3 million, what's the payoff? It's like zero. It's close to zero, right? We invested 488,000. We made 1.325 million, right? The whole point is to invest resources and optimize allocation scenario, right? So you invest a little bit less, but you make more. That's called synergy, right? You do more with less, right? It can't be everything. If you do everything, then the budget and the constraints and headcounts equal the investment. There's no payoff. There's no point in investing in this project. There's no positive result. There's no payoff. Doesn't make sense, right? But we pick the best combination of projects that maximize the benefit under the constraints, right? We had 39 people. We had 488,000 invested. We made 1.3 million. So it's a win. That's a huge win. So at first glance, it can look a little bit weird, but and that's why I went through too. Like I thought, like, is something off here? It's like, what's going on? But no, it really makes sense because you get the most benefit with the least investment, or the limitations that you are committed to, or your constraints. There's always a constraint with something. The constraint can be time, the constraint can be money, the constraint can be human resources. There's always a constraint. You don't have unlimited resources. Even, the richest people in the world, Bill Gates and what's his name, Elon Musk, they have limitations too, right? There's always limitations to everything. So you have to take all your limitations, understand that, and quantify that, and convert that into a process that is going to help you be successful, right? And you get more bang for the buck. It's called bang for the buck, right? So if I hit Control Enter here to refresh the cell, we can say what projects were selected and not selected. So these were selected based on the budget and the expected benefit. So again, how much you put into it, how much you get out of it, that's what you have to understand. That's what you have to quantify. And these are not selected right over here. So most of these things to the right, we're investing, what is this budget? 97,000, expected benefit 61,000. I'm not going to invest that. I'm losing money, right? Here's the expected benefit, 85,000, required budget 85,000, expected benefit 174,000. I'm not going to invest in that, and I'm not going to invest in this one. Expected benefits 53,000, and the required budget is 72,000. Doesn't make sense, right? But I'm creating this chart based on the required head count. So how big is the size of the circle is based on the head count. How many resources do we need? So this one down here is very interesting. We only need actually one person. So that one's pretty small. Required budget, 98,000, expected benefit, 119,000. So you make about a little over 20K, right? You invest one person. The resources is pretty minimal, pretty straightforward. Just communicate to the individual what needs to be done, and he or she will take care of it, and that is a done deal, right? That's done. And you make 20,000. So that makes sense, right? And all these in red, we're not going to engage in. Anything in blue, we will engage in. So why is Pulp the best choice? Remember, it's a linear programming solution because we're making binary decision outcomes here, right? So we're going to invest or not invest. That's it. Like 1 or 0, yes or no, true or false. That's it. One, it's a binary, right? So linear objective and linear constraints. So all these things are very linear. That's why we use the Pulp library. If there's more of a curvy linear or very complicated type of scenario, we would use a different type of optimization process. There's a SciPy Optimize, right? SciPy Optimize. I have a couple videos on my channel about that. You can check it out if you want. So we can use SciPy Optimize to optimize the decision-making ability or decision-making outcome, right? If it's more of a curvy linear or not linear type of problem. And there's a GrowBePy Python library. You can use that. That one you have to actually pay for if you're doing like big jobs. If you're doing small things, you can use it for free. I like SciPy Optimize. It's very powerful, very efficient, but you have to use the right tool for the job. I tell people all the time, like, if it's a linear programming job, use a linear programming tool. If it's a curvy linear job, use a curvy linear tool like SciPy Optimize. You have to use the right tool for the right job to solve the problem, to be efficient, to optimize your time, and to optimize your resources, your mental health, and your budget too, okay? But if you had like more of a curvy linear problem where there's lots and lots and lots of different variables, then you can use a continuous variable that's not binary or not integer, right? Like there can be many, many different outcomes. Then you use SciPy. If it's just two outcomes, either engage or don't engage, select or not select. We're selecting the project or not selecting the project. Just use a Pulp library. Very straightforward, very simple, very very efficient. So you have to use the right tool for the job. That's the point. So that's how you use strategy, resource allocation to do optimization in Python. So that's it, guys. I'm going to wrap up this video. I will post all my source code and share it with you guys. And you can download the source code in HTML format and run your own analysis in your own Jupyter notebook and see how this stuff works. Okay. If you have any questions, post it in the comment section below when I post a video later today. And that's pretty much it. Thanks for your time. Thumbs up, mission accomplished. And I will see you in the next one. Bye.